Okay, so the way we will start is first I'll do a short presentation. Um, can you see the presentation?
Yes.
Yeah. So I'll go through this presentation fast because I think we've already talked about Klepsydra before. So I will just go through the section fast, and then we'll open the tutorial examples a little bit and do it slightly more interactive, and see how it goes. Okay. There is no formal structure to this workshop at the moment. So I'll introduce with the core API. What you need, as we've said before, is like you need Ubuntu 18 or newer, GCC 11, 14 also works. I mean, GCC 14, C++ 14.
Plus, plus.
And for this workshop, I assume that you've already cloned Klepsydra SDK and you have cloned tutorial. So that's how we'll start with. So Klepsydra SDK core, if you see the architecture, it's this way. Like you have the base layer of the core, and then we have additional sections, which is the code generator. So you had the Python code generator installation messages you had seen. So that's the code generator. You have middleware connectors, so which allows you to connect Klepsydra core to either ROS, DDS, 0MQ, CAN, in fact, also CSP basically. And we also have some performance analysis tool, which is not a part of the community version, but we sell license for the performance analysis. And then we have additional language binding. So you can actually connect this to C or Node type of code. And then you connect this to your application, the application that you're actually going to work. In this demonstration, we are sticking to C++, so the language bindings don't come into play. Generally, when we have a Klepsydra SDK distribution, you have a developer station with the libraries and headers on which you develop. And then the licenses are also given for each of your target computers. So you can have the SDK running on your Linux computer, and then you cross-compile it for your RTEMS distribution or FreeRTOS distribution and so on. So the licenses, I mean, this is just administrative stuff, but I'm just putting it out. It's not so relevant to the workshop right now. Just a quick update on the support we have, like which computers, ARM, x86, and we also have non-Linux OS supported, like RTEMS and FreeRTOS. And we are adding support more as we keep on working. So what is the core API? So the core API is basically we have a publish subscribe model. For a publisher, we have two versions of the publish. One is a standard publish, which does a copy of your event. And there's a no copy version, which works with shared point smart pointers. So there are no copies. So it's faster.
That's the high performance version.
In fact, in the high performance version, we have two versions. One is the normal one and the no copy one. So,
okay.
And then you have a subscriber with which you can register listeners to take actions on the messages that you're receiving. And for these publisher and subscribers, you have something known as providers. So we have an event emitter, which is the base of the system. It's generally used for testing. So it's synchronous. So when you publish, immediately the subscriber is called and the action, whatever you have registered, is taken. So you don't, when you run with the event emitter, the idea is that you don't have to worry about the threads or memory problems and so on. So it's very useful for testing your application. Event loop, which is the high performance version, it is used in the case where you have many publishers and one consumer. So a typical example is you have multiple sensors and you want to take action on the data you're receiving from all these sensors. And a data multiplexer is the opposite case, which is one publisher and multiple consumers. And based on all these ideas, we have a derived API. So you can have a scheduler to schedule a task and run it periodically. You can define a service which basically is like at each, whenever an event happens, you can use it to execute some action, or you can define some task which keeps running in the background. So you do a startup and then periodically you execute the action which has been defined, and then you shut down. And we also have something known as an environment, which can be very useful for setting global properties. So you can have an environment with these 4 types of properties, 5 types of properties, which can be shared in your application. So you just share the environment, and then when you say get this property, you have that property for use in some other part of your application. I mean, in the tutorial, we don't talk about those derived APIs too much. We talk more about the core API because it's already such a heavy concept.
Mhm.
So yeah, so like I said, there are 2 main ways of processing your data. One is that you have on the left is the data multiplexer, which is a single producer producing events, and then you're taking action on this event with different consumers. The other one is the high performance event loop. So you have multiple producers which all publish to the same event loop, and the consumer consumes those events. And since they are in the same event loop, you don't have to worry about thread contentions and so on. Okay. So, yeah, just the same information in a different way. Basically, in your application, you could have sensors connected to your application with the CAN bus, some other sensors connected directly, some sensors connected with ROS, and all will work with your application. You don't have to worry about managing all those things. Okay. So the Klepsydra core uses some of the main ideas are that instead of using traditional multi-thread programming, we use stream-style processing. So instead of having a lock, worrying about doing a mutex lock, then checking the state and processing, you just publish data to a stream, you take data from the stream, and you reduce all the context switches, and that's what makes it faster. There are 3 main ideas in Klepsydra core. One is lock-free programming, second is asynchronous programming, and the third is dependency injection. So with lock-free programming, I guess, I don't know if you have an idea, you want me to explain slightly more or not?
Yeah, a little bit more if possible, yes.
Okay, so the traditional example, this figure which we have is that where in an airport, the plane doesn't stop in the air when the runway is blocked. It just checks the status of the runway. If the runway is busy, it does a loop and comes back and checks again. So it's doing its own task. It just periodically checks the status of the runway, and when it's ready, it lands. So it's the same idea. So you have an event loop running, and periodically it checks the status of the data. If there is new data, it takes an action. So everything is running in one thread, but in the event loop, everything is running in the single thread, and it just keeps checking the status of the event. So because you don't have context switches, things run much faster. You don't have to load data in and out and so on. And then the publish subscribe model is asynchronous. I'll talk about this in the next slide. And then the third idea is dependency injection, which also I will talk after this. So basically what we have is that, look, suppose you want to print hello world, a classic example. So you define a callback function which will process string data, which is what you have. And then in your main application, you define the publisher and the subscriber on the first 2 lines. You register the action which you want to take, which is the callback. And when you publish hello world, the event loop will call the listener, which is the callback, and publish this data. So you only worry right now about publishing the data. And when the provider picks up that data and it receives the data, it will print this to the screen, to the console. So that's the first part. Second is dependency injection, which is basically, like I said in the first part, in one of the first few slides, we have an event emitter and we have an event loop and we have a data multiplexer. All of those three can give you a different type of a publisher and a subscriber. What happens is that all three, when they give you a publisher and subscriber, you could use them in this same format. Basically, you take the subscriber, register the callback, the same callback, and you publish it. So what you're doing is that on the fly, let's say you had whatever the rest of your application which needs a publisher, you can easily switch from one type of publisher to the other. So in the testing mode, you have the event emitter publisher, and then when you want to really run your application, you switch to the event loop publisher, and then you have the high performance without changing the rest of your code. So that's what dependency injection is. So I'll talk quickly about the advanced features, which is that we have a code generator tool. It is YAML based. So essentially, you can define your data object which you want to publish as a YAML file, a YAML structure, and the code generator will develop C++ classes which can be used. There is a middleware connector API for ROS, DDS, 0MQ, and they also provide a Klepsydra publisher and subscriber. So in fact, if you have an application which uses the publisher and subscriber, you can easily use it with ROS, DDS, 0MQ, CSP, and so on. We also have a performance analysis tool. With this, you can do real-time analysis using REST API or with sockets, or you can also do offline analysis by storing all the logs in a file. And one way we do this analysis using the OpenMCT tool developed by NASA. So you get like this very nice charts with real-time performance, like what is the publishing rate, what is the CPU usage, and so on. So this is not part of our community version, it's part of our licensed version. But I'm just showing you how it works. The middleware API, so you define if you want it for ROS or TDS, and it will create mappers. So your classes which you define, let's say you want to publish point cloud data, you define a YAML structure defining the point cloud data, and the mapper will map it from a C style struct to a ROS capable message or a DDS type message, and so on. The mapping is done automatically, and so on. The code generator will do this generation of the C++ code. It helps. It also gives you helpers so that you can serialize this data to JSON or binary format. And it also has the mappers to the middleware. So essentially, if you have a YAML structure on the left defined like this, the code generator will define a structure on the right, which is like a float, double, and so on. You can also have std string, you can have pointers, you can have smart pointers, you can have vectors, and so on. It's quite good. And you can also have, let's say you define a class called, let's say, point, which has XYZ position, and then you define a second class called, let's say, point cloud, which is a collection of points. You can also do that. So you can use one user-defined object inside the other, and so on. I mean, this is a little bit advanced. You won't see this. It's used slightly in the tutorial, but yeah, I mean, it's when you play with it more, you'll see this more. And just an example of like Klepsydra SDK for user like intensive algorithms. The idea is that instead of parallelization, you're doing pipelining. So what that means is that, let's say a classic example of matrix multiplication. You have a series of matrix multiplication let's say A multiplied by itself gives you B, B multiplies by itself gives you C, and so on. The classic approach is to parallelize the matrix multiplication at each stage. So use the full CPU to parallelize the operation, get B as fast as possible, and do the same calculation with B, and so on. What Klepsydra does is that it pipelines this. So you do, whenever A multiplied by itself gives you B, you send it to the event loop. The event loop takes the action and does the next calculation. And these are separated into threads, and each thread can individually be parallelized if you want. So you can control, basically we call this like a 2D threading model, because you can control, let's say you can control that the thread 1 is parallelized to do vector matrix multiplication in using all the CPU cores, and thread 2 is not. You can control it this way. But this is a part of the advanced API. Just introducing the concept, but we won't talk about it much when we are looking at the code. So.
And do you have specific libraries for the optimization of the processor? For example, for the ARM, to use the multiple input commands, like to treat the vector multiplication, for example?
I mean, this is handled, the lower level. So it with the optimization, it does generally do it.
Via the compiler.
Depending on our application, sometimes we have to look into it deeper and then optimize it. But in general, it works. So I mean, we've done some benchmarks where we did this step, which is that this test, which is we had a series of matrix multiplications. The result of one matrix multiplication was fed to the next step, and so on. And we did this on multiple computers. So here, for example, when we say 10 steps, which is basically A multiplied by itself is step 1, which gives you B, and then B multiplied by itself gives you C, and so on. You do this 10 times. And when you do with OpenMP, publishing rate is defined as the rate at which the new A is generated, the input. So as you increase the publishing rate, the CPU usage with OpenMP quickly hits the limit, because it's using all the cores to process the matrix multiplication. And whereas with Klepsydra, it's a linear increase. And the throughput is the rate at which you get the output, basically. So at smaller steps, you don't see so much difference with the throughput. And you see that latency is slightly higher with Klepsydra, but there are ways to optimize this also. Where you see really the performance shine is when you start increasing the number of steps, and you see that the throughput, Klepsydra becomes better at handling higher throughput while keeping the CPU, let's say, reasonable, linear. Whereas with OpenMP, you quickly hit the limits, and then you cannot process any more data. So so that's basically the introduction of Klepsydra and quickly talking about the basic features and so on. And if you want to, like, I'll leave Pablo's contact information if you want to get in touch with him later. But we can now start looking at the code examples and so on. I don't know how you want to do this. Do you want to start with the tutorial examples yourself, or you prefer that I open the tutorial examples and talk through what is happening?
Perhaps I just have some questions.
Sure.
So you already answered to some questions that I had. So in the list that I saw at the beginning, Klepsydra supports some ARM processor, but I didn't saw the ARM processor that we will use in the Adrios project.
Which one is it?
It's in the others. It's A53 also. Huh?
It is supported. I think we need to update this. Yeah.
Ah, perfect.
Yeah.
And so, yeah, one of the function of your library is this communication. And do you support the communication between the FPGA part of the Xilinx system on chip and the processor?
So we have a team working on that right now.
Mm-hmm.
So as we have more info, I'll keep you updated on that, on the performance characteristics and so on.
Yeah.
Okay. Yeah.
Mm-hmm. Perfect. Good. Yeah. So I think one of the first implementation that I should do is a conversion of a raw image to a point cloud image, 3D image.
Exactly. Yeah.
So we can think to have a look on today on the example from this point of view.
Okay.
If
So,
makes sense for you.
Yeah. Okay. What I will do is I'll stop sharing the presentation and switch to the examples. Let's say. I don't know if you can see like a
Yes.
some code.
Can you
Mac
see it?
window.
Okay.
So let's say, I mean, this is the example one of the tutorial.
Hmm?
Let's see. So let's say here now your publisher could be instead of like a std string in your case, which is a raw data basically. So you could have it as a std string or std vector of floats.
Yeah.
But the idea is that you define it in terms of this raw publisher. Okay. And then you see that we have defined this on the left, this listener which takes action on your data, which is what we yeah. So this action, it doesn't depend on whether you have an event emitter or an event loop or a data multiplexer. So for testing your application, you define it in terms of the raw publisher and the subscriber. You write your code, making sure your calculations are done correctly.
What do you mean by correctly?
Basically, you're separating out the problem. You don't worry about the performance. You write you write your function the way with your unit tests, with your input data and expected output data. You write that without worrying about Klepsydra. The only thing is that, for example, the publisher here, example, it takes a publisher pointer, but the important thing is the string, right? And the listener on the left here, it doesn't need to know about the subscriber here. What it needs is the string, and what its expected output is that it prints the message to the screen. So when you write this function, you don't care whether there is Klepsydra running or not.
Mm-hmm.
So you do the similar thing with your raw data conversion to point cloud, which is that let's say your simple publisher is your sensor, which is taking data, which has let's say the libraries for your driver and so on. So it's taking data from the memory buffers and it's converting to floating point data or whatever. And then it just publishes that data. Your next step is taking this raw set of floating point data and converting it into a point cloud, which is a series of XYZ points. Again, this step, this conversion from floating point data to point cloud doesn't need to know about Klepsydra. So what you do is that your driver has a publisher of floating point vectors. Then your converter has a subscriber of floating point vectors and does the conversion to point cloud. And the output is publishing data. I don't know, it's so if you see, let's say, example, yeah. In the tutorial, you can have a look at example 3, I think.
Yeah, because it takes a vector of data. Okay.
Exactly. So what you see, what you have is that, okay, so here, vector publisher. What it is doing is generating random, let's say, pseudo-random whatever data, which is the vector. It is just publishing it. And then you have the sum vector data, which is calculating the sum. And using this publisher to publish the result. So here is the class I've defined, which does the transformation of vector to the result.
Mm-hmm.
And it only needs the publisher and the subscriber, one subscriber to receive the vector of floats and one publisher to print out the result.
Mm-hmm.
This here, what I'm defining is what to do with the output that you receive.
I didn't understand the last part that you said about event loop.
Okay. So here, okay, let's say I do this. What will happen is when I publish this data, when I publish a new vector, it will be received by this sum vector data on the subscriber, which will calculate the sum.
Yes.
And publish this. Okay. But now what I can do here is that, let's say I can define a new function here, which is xconst and I can either do std cout this one. I can do void, I don't know, and process some and do do something, I don't know, or let's say float. What I can do here is I can take so what it is now doing is that whatever is being published here as a sum is being received by this subscriber. I can do register listener, say sum. I can do I can also do something like this. So the third option, what I can do is that I can have I can connect another class to this instead, which takes the sum and does something else and then publishes it also. What happens in each case is like I said, this one doesn't know anything about Klepsydra. These in the functions inside, they don't know anything about Klepsydra. They do their calculations and they just publish the result. And what you do with the result is up to you.
Yeah.
If you so this is yeah, and then the next step, let's say, is that, well, this example is already using the event loop. But to start with, you could use the event emitter, so you don't have to worry about multiple threads and so on. It's the testing case. And this part of your code does not change whether you're using the event emitter, the data multiplexer, or whatever. So let's see. There it is. I think we have another example where we do example 5 in the tutorial, which is always the same thing. We are publishing a vector of floats, and then we do two operations with it, which is basically we get the sum and we also do a modulo. So get the let's say norm of the vector. And as you can see that here we are using the same class sum vector data, which was defined here, but now we are using data multiplexer instead of event loop. So this is what is called as dependency injection. You're switching from one behavior to another. But the idea is this, that you define your class to accept a pointer to the subscriber of the input and a publisher of the output. And then you register a listener which does the processing.
Where is the... where do you register? You said that you register the part that the processing.
Yeah, here.
Is this one? Okay.
Yeah, you could do it in multiple ways. You could also have, let's say, what's this data, and you do, let's say, instead of, I mean, if you don't want to do lambda functions, you could do it this way, and then you do bind. It's folder. I'm missing something, but it's essentially this. Basically, you're passing the pointer to this function by doing the register. And then, of course, in the destructor, you do subscriber remove listener. Okay. So what you could do is that instead of using lambda functions of this style, you could have this function. What you're doing is that you're converting the internal class member as a std function. So you need to bind, use std bind, and this placeholder. What placeholder does is that it tells the compiler that in fact this argument is a variable. So if you had a process data, let's say with const float, let's say this was your function, and you do float sum equal to something, and then you had output equal to sum divided by scaling factor. Here, what you would do is that you would say float so now what is happening is that the register listener function is still getting a function which has only one variable, one input parameter in this style. But the process data, which needs two arguments, is getting one, which is the std placeholder, which is the argument coming from outside, let's say the variable, and the scaling factor, which is here.
Okay, so we can pass some parameters to the function.
Yeah, so multiple parameters as well. I mean, you could do this in multiple ways. Right now, I've defined this as a member of the class, but you could have, let's say, a complicated thing, multiple inputs and so on. You could, well, right now this is a std vector, but instead, if you're publishing a class, you could also, instead of a std vector of a float, we are publishing point cloud data, then all the information is already inside there.
Are there some limits on the memory? So can I publish the full point cloud image, or should I output pixel by pixel, for example?
Well, you'll have to benchmark it depending on how much memory is using. What you could do is you could publish with the pointers, shared pointers. So it depends on the hardware that you have and the memory restrictions that you have. If your point cloud is obviously too big, you will run into limits yourself. Yeah, you'll see it.
Yeah.
In the tutorial, we also talk about the memory pool. There's a smart memory pool. In the initial examples, the memory pool is defined to be 0, so you're actually allocating memory each time you publish. But you could have a memory pool of 10 objects, let's say STD vector of 10. So sorry, you have allocate memory for 10 STD vectors, and then you will always use this pool to send and receive data.
I think I need also to spend some time to define a tester, so create some data to test my system, if I understand correctly the logic.
I mean, you can use the examples in the tutorial. There is also unit tests in the tutorial, so you can also have a look at those things. And yeah, you can experiment with those things. Yeah.
Okay.
We have also added we're about to add it to the main branch, but there is a chapter on the state machine also.
Yes, will you do a manual also for that?
Yeah, the manual is ready. It needs to be merged to the, I mean, it will be chapter 4 of this tutorial, basically. So there is a pull request which we have worked on. It's today or tomorrow it will be updated. So if you do later git pull to the KPSR tutorial, you will have the chapter 4 with like 5 or 6 examples.
Yeah, I saw that you put some code on the Git, but I didn't found the manual, in fact.
Okay, because it was chapter 4.md, it was a file. In the,
okay.
Yeah.
Okay, skip that. You have question? I had a look of the MQTT system, and there they have a heartbeat signal. So central system can check that everyone is still there. Do you have a logic like this one?
No, we don't. We don't have a heartbeat thing.
Mm-hmm.
No. But like,
though.
sorry?
Depending on the case, it could be easy to implement. Like you can have a function like using the subscriber and the publisher. You can like just have someone periodic task.
Mm-hmm.
You code the periodic task to every, I don't know, 100 milliseconds or something, just ping the different systems. Then you collect the result, and then they go. You have a event loop collecting the responses, and then once all the systems are corrected, you go like, yeah, everything's fine, everything's not fine. It's not natively, but I don't think it would be too hard to implement. Like,
I mean, the CPU usage depends on your listener function, how heavy your listener function is. So if you have a very lightweight listener function, which is just, let's say, you're publishing a Boolean, true or false, or something like that, or a integer, let's say, and your listener function is just checking that the integer has received or it has increased or something like a very small logic, then you're not adding any overhead, like not much overhead.
Yeah.
I don't need it, but I was just wondering if in the future we need to debug the system and we have a, like on the link between the FPGA and the processors, we want to see if it's constant. It could be an idea.
We don't have, at the moment, we don't have a middleware connecting to MQTT, but it could be possible depending on, like, you use Klepsydra on top of MQTT. So you send from Klepsydra to MQTT and so on. So then you have the advantages of MQTT with the performance advantages of Klepsydra. That could be looked into.
But I don't need it. I was looking for system that's work like the Klepsydra to better understand your logic, and I found this MQTT.
Okay.
But no, I think we'll not use that in our system. Okay, perfect.
Alessandro, can I make you a few questions? Like I don't know much about like what exactly are you trying to achieve? I understand that like you're collecting data through the FPGA, and then your goal is to from that raw data create a point cloud image, well, a point cloud information, right?
Yeah, we have a 3D camera. It's a indirect time of flight, so we will have like, if I'm not wrong, 8 images per image.
Mm-hmm.
Then we make a first calculation in the FPGA to reduce the amount of images.
Yep.
And then we'll go to the processor to we have some divisions, and so we will do them in the processing system. Mm-hmm. Then from that we convert it to a point cloud. And then there is a third partner in the project, I think the EPFL, and they will do from the point cloud 3D construction. No, they need to understand the orientation of an object.
I understand.
The real world.
Mm-hmm. All of these, like all the steps, will be done on the same device, right? Like the FPGA and everything will be done, FPGA and CPU, and the orientation detection will be done on the same device, right? There'll be no.
Yeah, more or less at the output of this system, we will have a space wire, so like Ethernet, and we will send out
just the output
vector.
Mm-hmm. I understand.
I skip some detail. I am not sure. I saw the algorithm to convert the 3D image to a point cloud some months ago, so I need to refresh. But
like this is the sky. Okay. Yeah, sorry to butt in. It's just like I wanted
no problem. But if you need more detail, we can go in that in the future.
Okay.
Some of the tests I did with I think I used a library with 3D, no, Open 3D or something. It was like point cloud library and so on. But I used the same style of code as in this example, which is I added subscribers of point cloud data or some custom subscribers and publishers to calculate orientation of an object from the point cloud. So I did the same thing, which is in this class. Of course, the class, the processing function was bigger. And let me see if I can find that example, if I can.
So Mandar, you already did the project. We can copy on you.
No, but I used a library, which is, it's not fast. So the if you can see a different file, or we are still seeing the same file.
I still see the same file.
Okay. Let's see. Okay, the example is not so clear, so if I show you right now the thing, it will look even worse. Let's see. I'll try.
Do you perhaps have the time to clean it a little bit and share it by email, or I don't know if it's possible.
The thing is, it's a very how do you say it's a lot of things, and it will take too much time, I think. I'm sorry.
Yeah. No problem.
I mean, I just wanted to show you how the publisher subscribers are being used, but it's not so easy to show that quickly. Let's say.
And just another thing, like this will done in obviously it will be done in real time, the collection of data, the raw processing. Like, is it that the business application, is it latency critical? Is it throughput critical? What, like, is it a mixed approach of them? Like, do you need the image faster, or do you need more images in with the same amount of computer power? Because that's an important question independent now.
I'm not sure. You should check. Perhaps there is something in the spec of the project. From what I'm not sure if in this project we need to catch the object. So if we need to catch it, the
latency, obviously, yeah.
Latency is important.
Yeah. But if it's only detection and
yeah, now we need to catch it. So I think we should not avoid to take too much time. And do you remember, Christoph, the frame rate is 10 Hertz minimum? That's something like that. Even slower.
Okay, I have
I'm not sure, but
code image. The buffer, at least I think you can see the new code. So basically, yeah, I have a subscriber and output publisher. It's similar, like I defined a function, which is what will do the processing, and at the end publish the result.
Yes, okay, good example.
Then, of course, if it's not a null pointer, I register, like I said, this, which is the input receive function.
with this bind function. Yeah.
So essentially, whatever logic, let's say the complicated logic is all here.
Yeah.
And then of course I have, I mean, this is defined, I mean, I have different classes and so on, like pointer to an algorithm, some complicated algorithm, which is doing the solve model, let's say. I think this is what the EPFL guys are working on.
Mm-hmm.
So I just call their function to solve the model, and yeah. But we could break this, for example, we could break this down into multiple classes where after normalizing the data, I just publish it here. I do a, let's say, publish normalized data, and somewhere else I have a different class which does subscriber to the normalized data, and then it calls this.
So we split the two algorithms.
Exactly. So what you can do is that when you have a complicated, because if you don't split it, then there is no difference between using Klepsydra or your method directly. Because if you're doing all the calculation in one chunk, then there is no advantage. When you split all the problems,
it's more inefficient because like you don't like it's not the whole computer is not being processed at the same time, and like so the idea, like what Mandar's saying, is the key. Like you split the calculation, and then you, for every different task of the pipeline, you allocate the resources that you require, and then you locate the bottlenecks and you optimize those effectively. That's how you get performance.
So essentially, let's say you write your first pass of your algorithm, let's say, and it's like this, and then you realize that in fact the scaling factor, this is not taking too much time. It's this part which is taking a lot of time, and everything else is just waiting for this to finish. What you could do is you split up the problem, and then you assign like very little memory and whatever to this part. And when you have split it up, you can assign a lot of memory for this, and let's say 2 CPU cores for this instead of 1. So you could basically parallelize this operation and make it run, let's say, with priority. But of course, when you do it with publish subscribe model, you're sequentializing the problem. So the parts which don't need CPU send the data quickly, they don't consume too much resources, and the parts which need a lot of CPU get the required resources, and then the waiting for new data is reduced.
It's like splitting the problem into different parts and then giving the resources, and then Klepsydra makes the. Normally, you could do this without Klepsydra. The problem is it would take a significant time developing the threading model, the like making sure that stuff don't interrupt each other. The value that Klepsydra adds is that this is splitting into different bits and customizing every bit to be optimal. Klepsydra simplifies. And then, like what Mandar said, like the dependency injection is particularly good, because when you do a production system, you want it to run as fast as possible, and you would use the event loop with a lot of data. But debugging multiple data sources in different places, all going at once, is awful. So like the idea is that like, okay, you can, in the testing, only for testing, you can use another version of Klepsydra which makes everything behave as if it was single threaded using the event emitter. So like if you having problems at some point in the pipeline, you don't need to run it with 1,000 million data and going crazy about like which data belongs to whom. you simplify the testing and the debugging, and effectively that reduces development time. I don't know if that.
Now, how do you measure the execution time of each line of the code? Mandar, you said, for example, the first part of the algorithm is light and the second part is heavier. How do you test for that?
Generally, what we do is we split up the problem, and then in the publisher and well, there are counters and data already there which measure the NQ time and the processing time, and they are there in those classes. In the tutorial, we haven't exposed those ideas. And then, of course, with the let's say license version, we also have this real-time monitoring, which allows you to monitor everything.
Yep.
But if you look in the code, there's a subscription, like the publisher class and the subscriber class have. So this is your publisher class, which is in the SDK, and it has publication statistics available.
And on this project, can we have that? Can we have then the full license, or how it works?
I think you should raise this issue in the meetings.
Yeah. Okay.
Because I think there are already some talks going on about it. So
yeah, I discussed with my project leader, and we will put this topic on the.
I mean, I think some conversations have already happened between Pablo and the others. So, but once you clarify with him, we'll give you the license and so on. Yeah. But yeah, like the subscriber class also has subscription statistics. It's a method already there.
Yeah, that will be useful in for the next part of this development.
So, like for example, you have NQ time, discarded events, just in case. Yeah.
Yeah, like when you program in Python, for example, you can also make statistic of your code.
Yeah.
Quite useful.
Exactly.
Perfect. So I think for now I have quite a lot to test then, to implement. Thank you very much for this explanation, this workshop.
You're welcome. Yeah. If you have any questions, feel free to write to us. Keep the support at Klepsydra in copy, and yeah, one of us will reply.
Okay, perfect. Yeah. So thank you very much.
Thank you.
Thank you. Pleasure to meet you.
If you later can send us the recording, it would be great.
Yeah, I will check that. Bye, everyone.
Bye.
Bye.
Bye.